Okay. All right. Let's get started. Is that a hand kind of Ben?
On the lab, can I ask you a lab question?
You can ask me a lab question. We'll see if I answer it.
It turns out it seems that our function generator, instead of 0 to 10 volts being the range where we should vary from, it's -5 to 5. So we're wondering, we're getting from the output of our integrator and the output of our op-amp are varying from 0 to 10 degrees, signal. So we're wondering how to move that down from -5 to 5, and have an offset of -5 volts. Is there a good way to do that?
Okay. So the question is, they have discovered that on their function generator, you've got it's not a 0 to 10 volt difference that makes a difference on the VCF. It's a -5 to +5. Okay. And then how do we finagle the integrator circuit and all the amplifier circuits and all that to do both positive and negative voltages? First step could be applying a DC bias. Second step could be in response to the following. You don't need to handle major changes to the output signal. So if you have a 1 kilohertz center frequency, you don't need to handle 800 hertz changes in it. You don't need to handle an error that's like 800 hertz. You just need to handle smaller errors.
You're saying it doesn't matter?
What I mean by that is go back and do your calibration and figure out how much of a voltage range do you actually need to handle. And you don't need to handle -5 to +5 if the magnitude of the error is small.
So the VCF, how exactly does it work? It depends on what you've actually got the frequency set to, right?
Mm-hmm. Okay, so the question is, how does the VCF actually work? And part of the lab is to figure out how that actually works. But does it depend on what you've got the frequency set to? It depends on which button you push, whether you're on the 1K center frequency or the 100 hertz center frequency. How much of a change in voltage on the VCF input results in how much of a change in the frequency? It depends on which is your center frequency. Excuse me. So, yeah, you're going to have to think some more. Other questions? Lab going well? Confused as mud? So, what should you start? What should be your initial duty cycle? What your initial duty cycle could be a way of applying a DC offset. So, what I have found, and oftentimes when I teach my classes, is that there's the transmitter and there's the receiver. And the transmitter can transmit all he wants, but until the receiver's on, it doesn't do any good. I can broadcast stuff till the cows come home, and until you get to the point in the lab where you understand what I just said, me telling you that, all you can do is write it down. Maybe if you read it later on, you can go back, okay, now I understand what you're talking about. You don't have to have your initial DC, you don't have to have your initial duty cycle of your output, your square wave output, be 50%. That doesn't have to start at 0. Okay? So that's a knob that you can use to tune your system if you want to use it. You don't have to handle large magnitude errors. The other deal is that use your head. Don't turn your brain off on this lab. If you find a spec in the lab that you want to violate, I'm all for it, but let me know first. Okay? So if we want to tweak something in a way that seems like it contradicts what the lab write-up says, tell me. Tell me why, and I'll probably say that's just fine, and we'll make the exception, and you'll still get full credit. Okay? Now, if you come back and say, well, I want to violate the lab write-up in the sense that I don't want mine to work, that's not going to fly too well. I'll say go right ahead, but just suffer the wrath of the greater. Okay. Other questions? Did you solve your access issue? Okay, so Jonathan has been pestering for a lab key. He works down at SDL, and he can't get into the lab at the times that he needs. So Heidi's working on getting him a key and has been pestering the key office over and over and over again, but apparently there's some snafu going on. So he's having trouble getting into the lab, and we can't think of any way to actually get him into the lab. So I don't know, should we have them email you times that they're going to be up here, if that would help? I mean, what times do you want to be up here? And let's see if anybody's going to coincide.
Early morning.
Anybody going to come at 6 a.m.? Anybody going to still be here at 6 a.m.? We'll put it that way.
I am planning on coming up tomorrow afternoon about 5-ish.
Okay. Anybody going to be in the lab tomorrow at 5-ish? I'll probably still be here. I'll let you in. Yeah, Tech Expo. He's already got a job. Okay. Other questions? Onward and upward? Okay. So now that we've talked about lab, let me just mention that you're going to have homework for Chapter 6. Like I said, I'm going to continue to remind you just so you realize I am lightening the burden on you. I have normally given out several homework assignments, and I normally have 2 homework assignments that I give out for Chapter 6, but I'm not giving you the other homework assignment, and I'm shortening this one down to 1 problem. And it's just that thing that I talked about last time, implement those C macros. So I'll post this on Blackboard. It'll be due in about a week. It'll be due after the lab's due. So you can panic all you want on getting the lab done, and then spend the next night all night doing the preprocessor. Please remember you have these 2 preprocessor operators available to you. The stringization operator, if you put a pound in front of a symbol, that expands to putting that symbol in quotes. And if you put 2 pounds between 2 symbols, that concatenates those 2 symbols together. So these are operators that are evaluated by the preprocessor. If you want to fiddle around and see exactly what they do, my suggestion is that you ask a preprocessor. Write some C code that invoke these things and see what the preprocessor output is by just using the -E in order to see what the output of the preprocessor does. Okay. Exam grading is underway. It'll take me a few days. Lab 4 due Tuesday. Lab 5 is coming. Think about reading Chapter 6 and 7. Because you've all read Chapter 6, right? Because we've already covered Chapter 6 in lecture. Okay. All right. Let's consider the following program here. This program is a file that I wrote called stacks.c. We're going to pick this apart and ask a few questions about what in the world is it doing. We've got int glob var equals 43, a global variable. Unsigned int star glob ptr equals null, a global pointer. Okay. Int main, where's the facilities for passing command line arguments? A local variable called local var. We initialize that to 0. We set globe pointer equal to the return of malloc. So unsigned int star malloc, and we pass it the size of the unsigned int. We dereference the globe pointer, and we set whatever the globe pointer points to, that memory location, equal to the address of main. So we're just treating the address of main like an integer. We're going to write into the memory location pointed to by globe pointer that integer. Okay. Then we're going to print out a bunch of stuff: the address of global variable, the address of local variable, the value of global pointer, the address of global pointer, and the contents of the memory location pointed to by global pointer. Okay. And then what do? We call main. Can you do that? Can you call main? Just because I did doesn't mean it's legal. What is this going to do? Wait, why are you going to call main? It's going to go to screensaver. Okay. This program will run for a while, and then it'll eventually die. Why will it do that? Let me show you what it actually does. Oh, there we go. So it's scrolling and scrolling and scrolling and scrolling, printing out a bunch of stuff, and you can see what it's all printing out. So you can see right here is the address of the Google. Oh, wait, it stopped. Do I have a break in here somewhere? Do I have a return 0 somewhere? Why did the program stop running? Ran out of memory. How did I run out of memory? Kept on malloc and malloc and malloc and malloc and malloc, and I ran out of heap. What happens on the heap when you malloc and then you don't have any heap space left? What does malloc do? Turns null. So why would that cause my program to crash? It would just return null. Try to write in null. How many times would I have to call malloc in order to run out of heap space? We'd be here for a while running a program. You have to allocate a whole lot of space. This did not crash because we ran out of heap. So why did it crash? Yes, we ran out of memory, but it wasn't the heap. We blew the stack up. How did we blow the stack up? Yeah, you had me last semester. You know why. Okay. We're going to figure out why it did that. Stack overflow. What happens? Why did this happen? Okay, so we're going to talk a little bit more about the mysticisms of the C programming language and how it executes on the computer. What we talk about today applies to the TS7200 board, but it also applies to any C program on any computer you're running. That program I ran on that tablet. Okay, so this is good stuff to know no matter where you're programming. Okay, how do we use the stack in a C program? You use it for local variables. Number 2, you use it to allocate it as allocatable scratchpad space for C functions. And then you use it as a shared memory location where you can share variables between function calls. Okay? So we're going to pick these 3 things apart in turn and show you how the stack is actually used. Okay, so number 1, local variables. Local variables are allocated to the stack. So like what we showed in that C code, there, we have a local variable called local var, an int. This variable gets allocated to the stack. Its location sits on the stack. If you have 2 different invocations of the function, each of them gets their own local copy. There is not a global address for every instance of a local var. Each variable for each invocation of the function sits on the stack at a different spot. Okay? The compiler will emit assembly instructions when it sees a declaration like this to adjust the current stack pointer to make room for this variable. Okay? We reference that variable relative to the stack pointer or relative to the frame pointer. We'll see examples of this. Hope you're feeling your oats for x86 assembly, because we're going to show some x86 assembly today. We'll be transitioning to ARM assembly next time. Okay. Local scratchpad. What do we mean by a local scratchpad? So, you know about registers, and whenever you're operating on anything in assembly, you have to load stuff into registers and operate on it. Okay? What happens if you're going to load into a register, but that register has valid data in it that you want to keep track of? Well, you've got to save that data. Where do you save it? Well, that's why we have a stack, because a stack offers us plenty of space that we can just put stuff in and reference later on. So we just use this as a scratchpad memory that we can keep track of and reference later. So when we're saving the value of a register that somebody else owns, what we want to do is take that value, push it onto the stack, use the register, and then before we're done, we pop the value back off of the stack and put it back into the register that we whacked, so that our caller is none the wiser. Okay, so what we just referred to is the fact a register might have valid data. Somebody else owns it. And I will be using this analogy of different people owning this. So we have a computer program, which isn't a person. We have functions that call each other, and they aren't people, but nevertheless I'm going to use an analogy as people. Okay, so a function calls another function. A function may own a register. So that guy owns a register that I want to use. I've got to keep from messing that guy up by protecting him, by making sure that I save any registers that I'm going to whack before I whack them, and restore them before I come back. Okay. There are conventions governing ownership. The convention governing ownership is a convention that's employed by a compiler and an architecture. We call these caller save and callee save registers. How we employ this convention, we partition the register file into two sets. One set we call caller save registers, another set we call callee save registers. There's nothing about the hardware that mandates this convention, but it's just employed by compilers so that when you write a function and you reference a register, you know which ones you've got to save before you use them, and you know which ones you've got to save before you call another function. Okay? C functions, functions call other functions, functions can be called by other functions. We have to keep that in mind. A function can play the role of a caller, and a function can play the role of a callee. Every function is called by some other function. Can you tell me a function that isn't called by another function? How about main? This is where you go into a job interview and they say, can you tell me a function in C that isn't called by another function? And they'll bait you into saying main, and maybe they'll even think that main doesn't get called by any other function. But you say, I know better. Main is called. It's called by the stuff in CRT0. So the code at CRT begin or CRT init or CRTI or whatever the names of those symbols, underscore start, that's the thing. So the start function or label is a function that doesn't get called. It just gets jumped to. But it has a function call to main. So main does get called. All the other functions you write, they all get called. Are there such things as functions which don't call other functions? Can you write a function that doesn't have a function call in it? We had better be able to write functions that don't call other functions, otherwise a program will never terminate. Okay? So, we have functions that get called, we have functions that call. A function can play the role of a caller when it's going to call another function. That same function plays the role of callee because your function gets called by somebody else. Okay? So everything starts at the function main. Main gets called by start. Main calls other functions. Those are the functions that you write. Okay? Your functions you write can be callers. They can be callees. Sometimes we want to look at them as a callee. Sometimes we want to look at them as a caller. And the painful part about callee and caller save registers is you've got to keep track in your mind. Am I thinking about my function as a caller or as a callee? Okay, let's look at this example code here. Suppose we've got a function called fn. It takes two parameters, a and b, and it just returns the sum of a and b. Then we have main. It has three local variables, x, y, and z. It initializes x to 3, y to 4, and just z we're using as a result. We do some other stuff, but eventually we call this function fn. We pass it the value of x and y. We take its return value and we put it in z. Okay, main is called by underscore start. Main calls fn. Fn is called by main, but doesn't call anything else. Okay, so these functions have various roles. Main or fn will never be a caller. It is only a callee because it doesn't call any functions. Main is both a callee because it's called by start and is also a caller because it calls fn. Okay, if you're a caller, what we're only concerned about with respect to saving registers is the fact is at that time where you're preparing to call a function. So we know that when a function that's going to call another function, somebody called it. And so when we deal with the fact that a function was called or when it is a callee, we deal with that towards the beginning of the function. Later on, when a function is going to call another function, we just worry about the preamble to the call. And that's where we deal with, or we're cognizant of the fact that this function is a caller. So in a few instructions right before a call is where we say this function is a caller. What do? Caller save registers are registers which are assumed to be overwritten when a function gets called. Okay? So if I am going to call another function, and I've got data that's sitting in registers, some of those registers I assume are going to get whacked, and then the convention dictates that some of those registers I can assume will not get whacked. Or alternatively, if they do get whacked, it's the job of the callee to save them and restore them before. So I can assume that that I can put data into a certain set of registers Those are the caller save registers. I can put some data into the callee save registers, and I can assume that if I call a function, when that function returns, the data that I put into the callee save registers will still be there. However, I also must assume that if I put data in caller save registers, those registers are going to get whacked. So I have to make sure that if I want the data that's in those registers to be preserved across the function call, I have to save them to the stack before I call the function. So this is the difference between caller save registers and callee save registers. Who gets preserved across a function call? Callee save registers, they are assumed to be preserved across a function call. So that way, if the function that gets called wants to whack a callee save register, it has to save it first, write to it, and then restore it when it's done. If a callee wants to whack a caller save register, it can just go ahead and whack it, because it assumes that the caller has already saved its contents, or that the caller doesn't have anything in there that it wants to be preserved. When we save the values, where do we save them? We save them on the stack by pushing them onto the stack. Which registers are caller save? Well, that depends on what registers you have. ARM is a different processor architecture than x86. So because of the fact we haven't talked about in gory detail the internals of the ARM architecture, I guess we have a little bit, I'm assuming y'all are a bit more familiar, or at least have been at one point, with x86. So we'll talk a little bit about x86. So on 32-bit x86, we have EAX, EDX, and ECX are caller save registers. EBX, ESI, and EDI are callee save registers. That is at least using GCC. Okay, so in the fn function, we need to load A and B into registers. So you remember fn takes A and B, calculates the sum of them, and returns it. So in that process, it'll have to load the value A and B into registers. Okay, which registers does it use? If it uses callee save registers, it has to push the contents of those registers, then use them, then pop them when it's done. If it chooses to use caller save registers, it just overwrites the contents of those registers. Okay, so the case is pretty clear for fn. It should probably use caller save registers, because that way it doesn't have to push them and pop them. Pushing and popping registers is a pain. We try to avoid it. It's unnecessary if you can avoid it. Okay. In main, we need to load X and Y into registers. If you remember, it passes X and Y to fn. So we have to load those into registers, and then in preparation to the call to fn. So we have to load those guys. What registers should we use? If we use callee save registers, we have to push them first. If we use caller save, we just use them. Okay, but when we call fn from main, if we use caller save registers and we want those values to be retained across the call, you must save them before the call. So if you want to load the values of X and Y into a register, and then you want to call fn, and then you want those registers to still have the values of X and Y in it after you're done with the call, and if you choose to use caller save registers, you got to save them and restore them. So this is kind of darned if you do, darned if you don't. So if you're using callee save registers, you've got to push them first. If you use caller save registers and you want them to be preserved across the call, then you have to save them first. This is just the unfortunate aspect of having a function be both a caller and a callee. So then what's the point? Well, there are circumstances in which it does save you instructions. Okay, so main kind of looks like this, where we've got, let's assume that R20 and R21 are caller save registers. You load into R20 the value X, you load into R21 the value Y, you save caller save registers, you have some other stuff to pass parameters, then you invoke a call instruction to call the function, you clean up the stack when you're done, okay, and then you pop R21 and pop R20, that's to restore your caller save registers. Okay, why does this help? I chose to use caller save registers so I wouldn't have to save their values initially. Okay, this helps because of the following reasons. I only have to save those registers once. So if I have multiple calls, if I'm saving the caller save registers, I'll have if I'm using callee save registers, I just have to save them once at the beginning of the function. If I want values to preserve across a function call, if I'm using caller save registers, I have to save them every time I call a function. I could have used callee save registers. Using the callee save registers, you only have to save them once at the beginning of the function and then pop them once at the end. So if you have multiple function calls, maybe callee save registers are better. Okay. The other point of why this helps is because if you have callees which don't call functions, then they don't have to save registers. They can just whack the call or save registers and call it good. So effectively, this optimization helps the least level functions in your function hierarchy. Okay, so our three uses of the stack. So we've talked about Scratchpad. We've talked about local variables. The third one is a shared memory location between caller and callee. Okay, C supports pass by value. We pass a copy of an argument to a function. How do we do that? You would use the C calling convention. Parameters are passed on a stack. So the point is that we push arguments one at a time from right to left, and then you push the return address. After that's done, you call the function. After the function return, the callee pops the return address when it returns. And then at the end, the caller will clean up the stack when it's done by popping off the parameters that are pushed onto the stack. Okay, so how this is managed here. So on the function call in main, where we're calling fn and we're passing x and y, we push R21 under the assumption that R21 has the value y. We push R20, which it has the value x. So what we're doing is we're pushing from right to left, the rightmost argument, then the next rightmost argument. So we push all those guys onto the stack in that order, and then we call the function by whatever instruction our assembly language supports, so branch fn in this case. Okay, and when we're done, we assume that, so what this does is that pushes the return address onto the stack, and when we're done, when fn is done, it'll pop the return address off of the stack. The parameters will still be there. When fn pops the return address, it'll jump to the return address, which is the address of this next instruction following the branch instruction. We'll pop R20 and R21 back off of the stack. We don't necessarily need to save their values under the assumption that we're just, so main, all that it did is just pass those guys to fn and called it good. It didn't ever use x and y after that. It just took the return value. So we pop the stack just to clean up the stack and get those values off of the stack. We throw those values away, adjusting the stack pointer to deallocate because we allocated. Okay? Mitch.
With variable argument list, how do you know?
Okay. With variable argument lists, the whole point of why the C calling convention was created and why you push parameters right to left is because the designers of C wanted to support variable argument lists. So you push values from right to left, so that way the uppermost guy is the rightmost argument, and this guy that's right next to the return address is the leftmost argument. There has to be at least some type of convention, and the varargs stuff manages that. There has to be some convention of what's pushed onto the stack and how big is it, and as you're popping things off, you can acquire things in that way. I am trying to remember. I think that there's a count that's put on there, but I'd have to look it up. Don't use variable argument lists. They're bad. They're ugly. They're very useful when they're necessary. Try not to use them. Okay. When we're dealing with stacks, when you deal with assembly language and functions calling functions, and you've got to deal with what's been allocated on the stack and what's where on the stack, drawing a diagram of what's going on really helps. Okay? So those of you who've had the 3720 from me have done this till the cows come home. Those of you who haven't, and this is going to be kind of new for you. Okay, so this is called a stack frame. Okay, so what we're doing is we're going to draw the stack as an array in memory. We're going to draw it upside down from what you usually draw in memory. So I draw stacks like this with the low addresses higher in the diagram, high addresses lower in the diagram. We draw various slots on this stack. Each slot is a 4-byte slot because typically we're pushing a 4-byte value. Okay, so stacks grow up. They grow from high addresses to low addresses. This is true on the ARM. This is true on the x86. What that means is the stack pointer points to the last value that you pushed, and when you push a value, you decrement the stack pointer by 4, and then you write to the contents that the stack pointer points to. So this is just a convention that several architectures use. There's nothing saying that you have to have stacks grow from high addresses to low addresses, and in fact, ARM supports funky addressing modes to allow you to do stack accesses from low addresses to high addresses. But we just use the convention that stacks grow from high to low. Okay. So in our example, when we're calling fn, and you remember we're calling fn with the value of x and the value of y, and we're assuming that we've loaded x and y into our 21 and our 20. This is what the stack is going to look like. So down here are high addresses, here's our low addresses. We pushed our 21, then we pushed our 20, and then we call, or we have that branch instruction that branches to fn, and what that does is it pushes the return address onto the stack. So this is the value for y, this is the value for x, then we have the return address. At the point where we begin execution of _fn, that's the label corresponding to the function we're going to execute, the stack pointer register that I've drawn in a box here with SP points at the return address. Okay? Remember, the stack pointer points at the last thing you pushed. It does not point at the next spot you're going to push something. Okay? So when you push something on the stack, you decrement the stack pointer, then you write to that location. When you pop something from the stack, you read from where the stack pointer points, and then you decrement the stack pointer. All right, fine. You increment the stack pointer. So you make the stack pointer go towards higher addresses. Understand what I mean, not what I say. Okay. When fn, the function that we're calling, wants to access the parameters that it was passed, what it does, it doesn't access underscore A or underscore B or symbols that are on the symbols that are defined in some global memory. It does an addressing that's relative to where the stack pointer currently points. So because the stack pointer up there is pointing at the return address, it's going to say, okay, I want to access the memory location that's 4 bytes off of the current stack pointer. So it'll say, here's the stack pointer, add 4 to it, and grab the memory that's there. Grab the data that's in memory at that location. And we'll say that that's A. So if we say stack pointer plus 8, that's going to be the address of B. How do we know that that's B? Well, because that's the second parameter that was passed. So I know where my parameters that were passed to me are because I know what order that they were passed. Because the caller pushes variables onto the stack left to, or from right to left in the order that's dictated in the function prototype. Okay, so here's the problem. Sometimes I need stack space to save intermediate registers, and I need it for local variables. So the stack pointer has got to adjust as the function executes. So at the point where I want to reference a parameter that was passed to me, maybe the stack pointer isn't pointing at the return address anymore. So that gets kind of clunky. So what we use is a convention called a frame pointer. That's another register that we point at where the stack pointer is pointing when the function gets called, and then we allow the stack pointer to do whatever it wants, to adjust and to move. So we use a frame pointer register to keep track of where the current stack pointer is at the time the function gets called. Now, the problem is every function uses a frame pointer register. Every function uses a frame pointer, so if you overwrite the frame pointer register, you've just messed up your caller. So this is in some sense a call ESAVE register. So what we have to do before we point the frame pointer register at our stack frame, what we have to do is we have to save our caller's frame pointer by pushing it onto the stack. So one of the first things you do when you enter a function is you push the frame pointer register onto the stack. That's your caller's frame pointer. So it's pointing to someplace on the stack below here. And then what we do is we move the contents of the stack pointer register into the frame pointer register. That causes the frame pointer register to point wherever the stack pointer is pointing. Because we pushed the old FP onto the stack pointer is pointing at that old value. So then we point the frame pointer at that old value. And now what we do is when we access our parameters that we were passed, we do it relative to the frame pointer instead of relative to the stack pointer. You don't have to use a frame pointer. Just most compilers emit code that does it. Okay. The other thing is when you're seeing code and you see references to the frame pointer, Sometimes you'll see I want to access the memory location at the frame pointer at the address indicated by frame pointer plus 4 or frame pointer minus 8. So if you're accessing past arguments, you have positive offset to the frame pointer. If you're accessing local variables, you have a negative offset to the frame pointer. The reason why is because the frame pointer is pointing at the last thing that was pushed, then you allocate your local variables on top of the stack. On top of the stack, it's more towards lower addresses, so it's a negative address from where the frame pointer is pointing. Formal parameters are positive offset. Mitch.
How would you not use a frame pointer?
How would you not use a frame pointer? Okay, so a compiler is smart enough to keep track of what my offset is, because the compiler emits all the instructions to say adjust the stack pointer by this much. So it knows relative to where it started, where is the return address and where are all the formal parameters. So you would just have at different locations in your code. Well, the stack pointer's at here. I'm going to access my formal parameter A. That at this point is at minus 16 off of stack pointer, or plus 16. Maybe at another location it'll be at plus 32 off of your stack pointer. So it'll just it'll leave in references relative to the stack pointer, but at different offsets. It just looks like it's accessing different locations because the stack pointer could change. You don't necessarily get a performance increase directly. You can indirectly get a performance increase by not using a frame pointer because it gives you an extra register. For x86, that's really important because if you have an extra register and you can do math on the frame pointer register instead of using it to hold all your addresses, then that's less loads and stores.
So why is the frame pointer used with the best educational standpoint?
Why is the frame pointer used? Because it makes your code much more readable. And the return on the investment of dumping the frame pointer usually isn't that great.
Most of the time you don't even look at what the compiler generates.
Most of the time you don't look at what the compiler generates, nor do you care if you turn on or off the frame pointer, how much performance increase is it going to give you. So, and on GCC, if you want to throw out the frame pointer, you have to use a specific optimization key called -f omit frame pointer that's on top of -03. So -03 doesn't throw out the frame pointer. You have to explicitly tell GCC, don't use a frame pointer. The other reason, the problem is if you, it can become a problem if you write code that doesn't use a frame pointer. Well, okay, there may be times where you can pull the pants down on the compiler and fool it, and it doesn't know how to calculate the offset from where the stack pointer currently points. So if you're doing really funky addressing, you might be able to fool the compiler. That might cause your program to mess up. But those would probably be rare circumstances. Usually a decent idea is to keep track of the frame pointer unless you really need an extra register. Like on the Arch Lab, for example, from last semester. Okay, so thank you, Avast. Go away. Okay. Example x86 in a simple program. So here, this is what we're saying. This is the same program as above, except for using temp instead of main. So we just renamed this to be temp, and we're going to have main call this. Okay. So now we invoke GCC-capital S copycons.c. This creates copycons.s. So what we're doing is we're just writing this C program. We're going to translate it into assembly, and we're going to look at the assembly output. And the other thing to notice is we are using the native GCC, not the cross compiler for this. Okay, so here's copycons.s output by GCC. We've got a whole bunch of assembly directives. _fn right here. This is where the implementation of the fn function is. So these instructions implement fn. LC0 here, this is a label, and we've got .ASCII, quote, Z is da 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 da. This is the string that you end up passing to printf, because inside temp we call printf and we pass a format string. It explicitly saves the format string as the format string itself to be parsed by the implementation of printf, and that's how it gets allocated. So temp is defined down here with all these various instructions. And we're going to pick this apart a little bit at a time. So looking at Fn. So here's my first question. Why is it underscore Fn and not just Fn? Well, this is part of what the C compiler does when it translates stuff from C to assembly. This is a very minor form of name mangling. So what it'll do is it'll tack on an underscore. Okay. Note, EBP is your frame pointer register, ESP is your stack pointer register. So we push the frame pointer. This is where we're saving the old frame pointer value. We move ESP into EBP, so that points EBP at the old value of where EBP was stored on the stack. So this is just doing what I had told you about before. So you're just setting up your stack frame. Then you reference plus 12 off of EBP. You grab whatever is at that memory location and you put that into EAX. Then you add 8 off of EBP and put that into EAX. And then you pop EBP and return. Which local or which variable is 12 off of EBP?
The rightmost.
So Mitch claims it's the rightmost. Anybody want to contend with him? Is it X? Is it A? Is it Y? What is that guy? Is it obvious from looking at the assembly code? Boy, it can burn your head a little bit. So this is why when you start parsing assembly code, you draw stack frames. And you are going to have to draw stack frames, and you're going to have to draw stack frames until you're blue in the face, and Lab 5 is going to make you draw the stack frame of an interrupt service routine, and it's going to drive you bananas. Just be ready, okay? But you'll learn a whole ton from it. Okay, so stack frame. If you remember when we called Fn, we pushed the values right to left onto the stack, and then we pushed the return address. Okay, so this is what we have. We pushed B, then we pushed A, and then we have here the return address, and then here this is the previous frame pointer, because the first instruction up there is to push EBP. So then we pointed ESP, or that when we pushed EBP, that pointed ESP at this location. When on instruction 2 we move ESP into EBP, that points the frame pointer register at this location. So what is located at which offset from the frame pointer register? 0 off of EBP indicates this previous value of EBP. 4 off of EBP is the return address. 8 off of EBP is the parameter A. 12 off of EBP is the parameter B. So now, having this diagram, it's a little bit more obvious what MOVL 12 off of EBP into EAX is doing. So we can just say, okay, what's that 12 off of EBP? EBP points here, 4, 8, 12. That's the value B. So I'm going to move the contents of the memory location B into EAX. And then over here, I'm going to add 8 off of EBP. 8 off of EBP is A, so I'm taking A and adding it with EAX, which has, from the previous instruction, the value B. And now I'm going to get that into EAX. When I'm going to return a value, I just leave it in EAX, so it's good that it's already in EAX. I pop the frame pointer register, and I do a return. So popping the frame pointer register, what that does is it just takes the previous value of EBP that's on the stack, and it puts it back into the EBP register, so that's our caller's frame pointer. Doing a return pops the return address off the stack and causes us to jump to wherever that instruction indicates. Okay. What doesn't this stuff do? It pops the return address, but it does not pop A and B off the stack. That's the caller's job. Now what we want to do is look at temp. Okay, so this is the caller. So here we have this big old stack frame here. So the stack frame doesn't immediately appear. We'll build it up as we go through this. Okay, so instruction number 1, push the frame pointer. Over here we start with a return address. How do we know we have a return address on the stack? Because this is a function. It got called. Every function that gets called has a return address. Okay? So we know that there's a return address on there. We weren't passed any parameters. There's other stuff on the stack below here, but we don't care what it is. So we have a return address. First thing we do, we push EBP. That puts that onto the stack. Next thing, we move ESP into EBP. So that points the EBP register right here. At that point, ESP and EBP are both pointing at this location. Next instruction, subtract 24 from ESP, so that moves the stack pointer up to here. We now have several slots on the stack available for doing things that we're going to need to do later on. So ESP is now pointing here, EBP is pointing here. We can have positive offsets from ESP, negative offsets from EBP. Positive offsets from EBP would be accessing our formal parameters, but we don't have any in here. We move the value 3 into -4 off of EBP. -4 off of EBP is this slot right here. What are we moving the value 3 into there? Well, that indicates that this slot right here is a local variable that we initialized to the value 3. What local variable is that? And we have X and Y, okay? One of these guys is X and one of these guys is Y, and what you do is you just flip back to your C code and you see which one was the 3 and which one was the 4. You don't see X and Y in here because they're local variables. They are named as -4 off of EBP and -8 off of EBP. Intuitively obvious, right? But that's unfortunately how you have to keep track of them. You have to figure out which guy is what based on context. So 3 and 4 get moved into -4 off of EBP and -8 off of EBP. Then in this instruction, we move -8 off of EBP into EAX. So that gets our value 4. Then we move EAX into 4 off of ESP. So that moves 4 off of ESP. So that moves that value there. So what did we do here? So -8 off of EBP into EAX. So that's the value 4. We move the value 4 into EAX, then move it into +4 off of ESP. So the value 4 gets written right here in this slot. Okay. The next thing we do is we move from -4 off of EBP. -4 off of EBP is this guy. -4 off of EBP is this guy. So that's the value 3. We move the value 3 into EAX. We move the contents of EAX into the location pointed to by ESP. The location pointed to by ESP is this right here. So that's what we're doing. All this is doing is it's preparing a function call. The next thing that we do right here is we have this call instruction _fn. The call instruction pushes the return address onto the stack. Where's the return address? How do we know what the return address is? Let's suppose you were writing this code by hand. Do you have to calculate the return address? No. Thank heavens for assemblers and linkers, okay? But it's just the address of this move instruction, the instruction that comes next. Okay, so that's what we're doing to prepare the call. So we're going to go and I've got notes that basically summarize that process here. So this just repeats and just has written down here everything that you're going to need to understand, all that blah, blah, blah that I just said. Okay. Now if we look at the next set of it, okay, so after that, we've got the stack all prepared. We call a function. So this is what the stack looks like when we're calling the function. We've got a bunch of other stuff down below on the stack. These are the values that we copied up to 0 off of the stack pointer and 4 off of the stack pointer. So, and then we did the call fn that pushed the return address. The stack pointer is pointing now here, and at this point we start to do the code that's over in fn. Okay? So this is, and this portion of the stack, there's other stuff below it, but this is the only portion of the stack that fn cares about. And it had better, well, ignore everything that's on below it. Okay? But this is what the stack is, and it's all ready for fn to be invoked and to be run. Okay, so then when we're running fn, what does it do? Well, we already talked about that. It pushes the frame pointer, it accesses the formal parameters, adds them together, and returns by popping the return address off of the stack. Then we end up control coming back down to the bottom of temp. So then what temp does is it calls printf by pushing some other parameters onto the stack. The call to printf looks like just a call. There's nothing magical about the fact that printf has a variable argument list. It still just pushes parameters right to left on the stack and then does the call to printf. Okay? So after that, the caller cleans up the stack. How does the caller clean up the stack? Well, on there we have inside temp we have a return 0. So in order to return 0, we move the value 0 into EAX. Then we have this leave instruction and the ret instruction. What does the leave instruction do? The leave instruction is kind of like a backwards, move the frame pointer into the stack pointer and pop the frame pointer register. So what it does is it undoes the stack allocation by taking the contents of, so what it'll do is it'll take the contents of the frame pointer is pointing at the old frame pointer, it says move the stack pointer to that location, and then pop the frame pointer into the frame pointer register. So what it'll do is it'll just deallocate everything on the stack by moving the stack pointer down, pop the frame pointer register to restore our caller's frame pointer, and then it'll do a ret instruction there, and that causes it to return to whoever called temp. Okay. So we talked all this mumbo jumbo about caller save and callee save registers. Did you see any callee save and caller save registers in that mess? Did we have to save any caller save or callee save registers? Well, did we use any registers? Okay, so we used registers. Why didn't we have to save them? No, this is not undone by the magic of fantastic linkers and assemblers and other nice tools. There, in the assembly code, if you have a register that you're going to whack and you need to save that register, you have to save it somewhere. There has to be a push instruction. Did we have a caller save register instruction in there? Didn't see it. Why? We don't need it. Why? Because your compiler is a great tool. When it figures out what registers it's going to allocate, it tries to manipulate how you save information and use information so that you don't need data to be preserved across a function call. And why do we do that? So we don't have to save the caller save registers. So we saved EDT before we wrote to it. So that, in some sense, is like a call eSave register, because the frame pointer register has my caller's frame pointer in it. If I overwrite the frame pointer register, I had better keep from messing up my caller by saving it first and restoring it at the end. So that, in some context, is a call eSave register. When you write to EAX, that's a caller save register. So when the caller is going to have a value, it uses EAX and it calls a function. Why don't I need to save EAX before I call the function? Well, because I don't assume that the value that EAX contains gets preserved across the function call. I just make sure to steer the values that I store into the registers so that I don't assume anything needs to be saved across the function call. That's good design on your code to keep from having to save the contents of registers. Okay. So I just end these set of notes with a few words about when do you need to save stuff, why do you need to save a caller save register, and why do you need to save a call eSave register. One last 2 bits is in stacks.c we showed this program. And we said it dies. Why does it die? We said it dies because of the stack overflow. It has a stack overflow because we have a recursive function call to main here. What happens when you call a function? Push right to left, push the return address. This does this infinitely. So you keep on pushing and pushing and pushing and pushing and pushing, and you never pop because you never return. So you have a stack frame that has a whole bunch of local variables that initially looks like this. You call main again. You've doubled the size of the stack. You call it again, triple, quadruple. Well, it doesn't actually triple. You just keep on adding this much junk. You add it again, you add it again, you add it again, and you add it again. Eventually you get to the point where your stack overwrites your heap and your operating system says, "God, whack," and your program dies. Okay. I don't know how to do the I know how I spell it. Please come and talk to me if you're confused about your lab. Lab 4 can be horribly confusing. Please do come and talk. I want to help. 3:30 to 5, I'm in my office today.
Dr.
Yes, sir.
That assembly code you have that was preparing for a function call, it just moves the values in directly, just moves up into ESP rather than doing an actual push operation.
Okay. Why didn't it do a push? Because it takes all of it calculates how much stack frame space it needs right at the beginning, and it allocates it all in one fell swoop with a sub. Subtract from, so any space you'll need for parameters, local variables, everything you need for the whole function, it says, I need 24 slots on my stack, so I'm just going to allocate it all at once.
So why doesn't it just wait until it can do that and then do it actual push?
Push instructions take, for some silly reason, more time on an x86 than subtracting and writing.